Hello everyone! In this Ansys how-to video, we will show you how to perform one of the most fundamental linear dynamics analysis, modal analysis. The need to determine the natural frequencies of a structure can apply to many areas of engineering. Some examples include Tacoma Narrows Bridge, bladed disc, or valve body. Considering the dynamics effect in design is quite critical. In this video, we will focus on free vibrations or modal analysis of the mechanical systems. Let's go! Modal analysis provides valuable insight to the dynamics characteristics of the structure. It is a linear analysis that doesn't utilize any excitations or loads. Mode frequencies are dependent only on two things: stiffness and mass. Modal analysis provides engineers with information regarding how the design may respond to different types of dynamics loading and can be used, for example, to avoid resonant vibrations that can be harmful to the structure. That is why the modal analysis is the most fundamental of all dynamic analysis. It is the basis of all other linear dynamics analysis, such as harmonic, response spectrum, or random vibration. Let's see how we can calculate natural frequencies and mode shapes. The linear equation of motion for free undamped vibration is mass matrix time acceleration plus stiffness matrix times displacement, where m is the mass matrix and k is the stiffness matrix. If we assume harmonic motion, the displacement and acceleration vectors can be expressed by these two equations. Substituting displacement and acceleration back into the equation of motion, we can get the eigenvalue problem. Solving for the first part of this equation gives the natural frequencies omega, and solving for the second part of this equation gives the mode shapes phi. The eigenvalues are the square of the natural circular frequency of the structure omega, and eigenvectors are the corresponding mode shapes phi. In the example of the simple vibrating beam fixed on the both ends, if the beam displays a mode shape of half of the sine wave, it would be vibrating in modes 1 or 2. If the beam displays a mode shape of a full sine wave, it would be vibrating in the mode 3. Natural frequencies Fi can be then calculated as Fi equals omega I over 2 pi cycles per second. The eigenvectors represent the mode shapes obtained when the structure is vibrating and frequency Fy. The participation factor and effective mass obtained from a modal analysis can give an idea how the design will respond to different types of dynamic loading. Participation factor measures the amount of mass moving in each direction for each mode, and it can be calculated by this equation, where d is the unit displacement spectrum in each of the global Cartesian directions and rotation about each of the axes. In Ansys Mechanical, the participation factors for each direction is reported under solution information or by looking at the solver output. A high value of the participation factor in a direction indicates that mode will likely be excited by forces in that direction. Some modes may contribute more than others depending on the mode shape and participation factor value. If, for example, we know which mode may be excited in a particular direction, that can help in design assessment since we know what the frequency and mode shape is. Thus, by looking at the ratios, we can identify the modes that can contribute a lot to the structural response if excited in a particular direction. The effective mass is a measure of how much mass is associated with each mode. When we use the default mass normalized approach, the effective mass is equal participation factor squared. Ideally, the sum of the effective masses in each direction should equal to the total mass of the structure, but that will depend on the number of modes extracted and how the structure is constrained. The ratio of effective mass to total mass can be useful for determining whether or not a sufficient number of modes have been extracted. The material near the supports is generally less likely to move, so effective mass will be smaller than actual mass of a structure based on how much material is located near fixed supports. In the example, we can see that about 73% of mass is associated with modes 1, 2, and 6, which means that these modes are going to be excited by forces in x direction of the Cartesian coordinate system. Let's go and see how we can do modal analysis in Ansys Mechanical. In this demo, we will show you modal analysis of the metal frame and how to get modal frequencies and mode shapes. Additionally, we will look at the participation factor and effective mass and see the effect of number of extracted modes on these quantities. Insert modal analysis system on the project page. Import geometry. Check material. Structural steel is assigned material by default. Insert mesh sizing under mesh and set the sizing to 0.05 meters. Geometry is suitable for sweep mesh, and we want to ensure that there are at least 2 elements through the thickness of the frame for the better accuracy. Insert fixed support and scope it to the entire perimeter of the frame. Under Analysis Settings, we can specify maximum number of modes to find, and under Limit Search to Range, we can specify the frequency range. In this example, the number of modes to extract will be the default number 6, and the default frequency range will be used. Next, solve the model. Once you get a solution, the table of mode numbers and frequencies is available. Right-click and select all. Right-click and create mode shapes. Notice that 6 total deformation results are inserted in outline tree automatically. Right mouse click on the solution and evaluate all results. Click on the total deformation. This is mode 1. The tabular data shows corresponding natural frequencies. Let's look closer into the participation factors and effective mass. Click on the solution information and under Solution Output select Participation Factor Summary to see participation factor and effective mass tables. The participation factor is used to determine how much of the mass of the certain mode is moving in the same direction as the excitation. A high value in a direction indicates that the mode will be excited by forces in that direction. Participation factors are available in all 6 directions, as we mentioned previously. In this case, for example, mode 5 is mode that is making a meaningful contribution to the response in x direction and will be excited by forces in that direction. Let's look at the effective mass. Effective mass is giving the amount of mass moving in a certain direction for a given mode. The value is higher for the more prominent modes. In this example, if you look at the ratio of effective mass to total mass, about 13% of overall mass is moving in the direction of the mode 5, which is x direction. The sum of the effective mass is a good indicator if enough modes are extracted. The effective mass in each direction should add up to overall mass of a structure, but that would depend on how the structure is constrained. Let's see what happens if we extract 200 modes. Under Analysis Settings, set maximum number of modes to find to 200. Next, solve the model. Next, see the participation factor and effective mass in the participation factor summary. More prominent modes can be identified by the higher value of the effective mass. As we can see, about 63% of overall mass is moving in x direction, comparing to the previous case where only 13% of the mass was moving in x direction. We can see a higher percentage of the actual mass moving in x direction when 200 modes are extracted, But it is still not 100% of the actual mass. Why? In this model, there is the fixed support around the perimeter of the frame, so the material near the fixed constraint won't move and effective mass will be smaller than the actual mass. This concludes the demo. Now let's summarize what we learned in this video. Modal analysis calculates natural frequencies and mode shapes of the structure. Participation factor shows the most prominent modes in a certain direction that will be excited by forces in that direction. The effective mass can be useful for confirming that enough modes have been extracted for further analysis such as harmonic, response spectrum, or random vibration. I hope that you find this video informative. Please share the video, post your comments, and subscribe to this channel to stay updated. Don't forget to visit courses.ansys.com to discover more useful courses.